Hello everybody, thank you for attending RSA webinar today. My name is Artur Kosakowski and I will be running today's presentation together with my colleague Rafał. The topic of this webinar is time history analysis. Because of the complexity of the covered topics, I'd like to start with the description of the theoretical background of time history analysis, and then I'll try to demonstrate how to define it in Robot. The webinar will be the combination of slides and live views of Robot, followed by Q&A session. As the microphones of the attendees are muted, please submit your question using the question box of the GoToWebinar panel. In this webinar, we'll focus on basic assumptions of time history analysis in Robot, definition of dynamic excitation, using time history as analysis for various dynamic effects, types of results available for time history analysis, exploring time history analysis results, and the next webinar will be for moving loads. On this slide, you can see the basic equation of motion. As you can see, this is exactly the same equation as presented during our previous webinar for FRF and footfall analysis. Let me remind you that for dynamic analysis in Robot, mass matrix is constant and it doesn't change during the analysis. The same applies to the stiffness matrix for all types of analysis, with the exception of static nonlinear and nonlinear time history analysis. As in Robot, you decide on the mass matrix in the model analysis parameters, you have to define it before a time history analysis case. The model case is also needed for definition of additional masses or load to mass conversion. In addition, time history analysis requires the access to the results of model analysis, and its precision depends on number of the calculated modes when the model decomposition method is yet selected. As you can see, the number of available methods is different from linear and nonlinear time history analysis. For the linear one, the methods are listed in the order they have been implemented in the program. For the nonlinear time history analysis, only two last ones, HHT and Newmark acceleration, are available, and they will be automatically set when there are any nonlinear elements in the model, such as tension-only bars, or when you mark p-delta or large displacement checkboxes. For the model decomposition method, damping is directly assigned to modes. Mind that if not entered, the last value of damping is used for remaining higher modes. In the situation, as on the left picture, all modes will have 2% damping assigned. For other methods, damping is calculated as a linear combination of stiffness matrix and mass matrix with the use of alpha and beta factors. The dialog visible on the right-hand side allows you to calculate them based on pulsation and relative damping for two representative modes. Linear viscous dampers can be defined as properties of supports, releases, and compatible nodes on the damping tabs of their definition dialogs. They are supported only in the two methods of time history analysis marked on this slide. Nonlinear viscous dampers are not available in the current version of Robot. Mind to match the time step with the speed of changes in loads. If you have fast-changing loads, the time step should be small enough to secure the precision of the solution. The same applies to number of divisions for all but the model decomposition method. Excitation is defined as forcing function with time as its parameter. This function is then assigned to already defined static load case as a multiplier for whatever kind of loads is defined there. It can be a force, but it can be an imposed displacement of a support as well. In addition, you must select sort of virtual load cases named as directions, which are intended to simulate earthquake with time history analysis. For these cases, the forcing function is defined in SI units, which for acceleration is meter divided by second squared, regardless of the unit set in robot job preferences, which is especially important to know for those of you using American units or for accelerograms defined as relative to the gravity value. The time function diagram shows time on the horizontal axis and forcing value on the vertical one. As the diagram is built from values given for indicated time points with linear interpolation for the immediate values, it is recommended to provide sufficient number of points to obtain the exact shape of the function. You can also use the formula to generate these points automatically with use of the Add Expression button. Let's focus on some examples now. First, I'd like to show something related to the topic of the previous webinar. As you already know, watching it, footfall analysis can only be used for some typical situations, being mainly a single person walking. If you, for example, want to simulate behavior of a crowd, you need to use time history analysis instead. To determine the forcing function, you may want to look at the SCI code, which provides the equation shown on this slide. It is similar to the one for footfall analysis, but with larger number of harmonics and crowd rather than a single person, which is often assumed as 2 persons per square meter. The table in the bottom right corner displays Fourier coefficients and phase angles for different types of activities. For a normal jumping scenario with 1.5 Hz frequency, you can define the time function using the Add Expression tool I introduced a moment ago in the way shown on the currently displayed slide. T in the displayed formula stands for time, whereas the other factors are taken from the table shown on the previous slide. Mind that for this function, radians are used instead of degrees. Depending on the actual type of jumping, the values of peaks may be different, as well as the length of the flat segments. Among them, however, the values of the flat segments are close to zeros. Let's see how to define something like this in robot. So I'll now try to switch to robot. Okay, and I have a case 14 defined here, and we can see the loads defined in this case. And now I will define the time history analysis. Okay, I already have the model case defined. So, okay, time history analysis. I will select model decomposition method, and I will define damping as 1%. Okay, that will be for all modes. And the time step will be like this, division 10, and the time will be 15 seconds. Okay, and then I will define the function. I will call it jumping. And then we switch to points, and I will go to, before that, okay, let me close that dialog for a moment. I need to do one more thing. I need to go to my slide, and I'll need to copy. I need to copy the formula that I defined for the function on the previous slides. Okay, so we go back to time history analysis. Okay, function definition. Okay, jumping. Okay. And we go to points. Okay, points. Oh, sorry, I'm jumping at. I need to go to add expression, of course. Add expression button, and now I can copy the formula from the slide. And beginning time is 0, end time is 15 seconds, and time step that's going to be 0, 0, 1. And we need to use radians. And okay, you can see that now the program calculates the points, and we have the function, so we can close that. We can go to case 14, assign it the function that we defined. So we have the time history analysis defined, and I think that I need to set it again here. Okay, that's going to be okay, and model is 1% again. Okay, 0, 1, and okay. So we have time history analysis defined, so we can calculate that. Each of the steps, for each of the steps, the program now calculates and saves the results. I'm not going to calculate each of the model that I wanted to show today, because as you can see, the number of steps needed for having the precise solution is large, which requires a bit of computation time. But we can see that on looking at the first example. Okay, so a moment to finish the calculations. So we have the results, and I will now focus on time history case. Okay, I will now display the. Okay, so you can see we have the kind of the results which are the same as for static load case, but time history analysis is a compound case. Simple load cases, and you can see that you can move the components, and you can see the change in forces, and you can also see the change in the results. In this case, the deformation. Okay, so we may also have a look at the tables, for example, forces. Okay, so you can see that when we select the case 15, time history analysis, we have the results for each single component. But as it is a case that have many components, it behaves in the similar way as moving loads or code combinations. So we have automatically created top and bottom envelope filters for tables, and we can use them looking at the text results. Okay. In addition, we've got the similar results as for footfall analysis, of RFF analysis. We have time history analysis diagrams. And for example, let's have a look at the jumping function. Okay, you can see the jumping function as defined in that parameters of time history analysis. And we can add some additional results. For example, vertical displacement of node 16. Okay, we can add the display of this. Okay, you can see. And we can also add the corresponding acceleration. We can change the color, for example. Okay, so we display that on our diagram. By default, the scaling is to the largest value, but we may switch off this scaling, and now you can see that each value, when you click on the table, has got its own units. And we may also add the information about maximum and minimum value for the displayed results. Okay, so let me go back to the slide. And let's see another example of use of time history analysis. Now we will try to model a rotating piece of machinery as two perpendicular forces with 90 degrees phase angle between them with use of two models. The first model represents the steady state condition, steady rotation, whereas the other is intended for the transient condition, starting or stopping rotations. Okay, so I will switch to robot again. I will open another example. Right. So I will define two new static load cases, Fx and Fz. And now I will define two forces. Horizontal one, in the first case, apply that to node 47. Okay, we may see the values. Okay, and I will switch to the Fz case, and I will define the vertical force of the same value, 0.1, in exactly the same node. Okay, so we now define a time history analysis. First, I need to define model case with default parameters. Then I can select time history analysis and okay, model decomposition method again. But we will have a smaller step this time, and end time that's going to be 2 seconds. Damping for mode 1 and all next mode will be 0, 0, will be 5%. And we'll define two functions, sinus. Okay, and again we go to act expression and this 10 Hertz and multiply by time. And beginning, okay, and time that's going to be 2 seconds, and time step zero, 0, 1. Oh, is 0, 1. Okay, and you can see that's our function. And we also define another function, cosinus, and this time the function is going to look like this, and the same parameters, end time is 2 seconds and 0, 1. Okay, so I have two functions, and I will assign the first one to case 5 and second function to case 2. Now I can run the analysis. This time that's much faster. And okay, first let's have a look at case 5. Let's have a look at time history analysis. And okay, if we have a look at the components again, you will see that the situation is that when one force increases, the other decreases, and we may also have a look at the diagrams to see the effect of these forces. So you can see the structure moves horizontally and the roof moves vertically as well. Okay, so let's have a look at the diagrams for time history analysis. This is probably the most interesting part. So we may first have a look at the functions, and you can see that this 90 degrees phase angle shift on these diagrams. This time that was done defining sinus and cosinus function rather than the angle itself. And I will add the display of vertical displacement of node 47. Okay, and I will also define the vertical displacement of the same node. I will remove the functions. I will replace them with displacements. So you can see the difference in the vertical and horizontal displacement of the node where we define the unbalanced rotational mass. Okay, I will now show you the second example, which is like starting and stopping rotating machine. Okay, so let me show the model. In this model, there's similar situation. We have static load case with two static load cases with two forces defined, and that's a very simplified model of the foundation, machinery foundation. And in this model, we have the elastic releases defined at the supports. And then when we go to the time history analysis results, diagrams, we can see both the forces and the displacement of the node where the force is defined. Okay, so you can see how they look like. And I will switch off the automatic range because I want to show you that actually this green line, which represents vertical displacement, you can see when you start the machinery, the values of displacement are larger than during the steady state. The same happens when you stop the analysis. Okay, let me go back to the slides. Time history analysis can also be used to simulate some accidental situation. For example, as described on the currently displayed slide, when there is a break in the cable that anchors the mast. So I will again go to robot and I will open the model. Oh, let me first open the model where there is the first point from the slide, that is impact of weight falling on the object. Okay, in case 2, there is a certain force defined that corresponds to the weight of the object falling from a certain height to the floor. And in this example, we have 3 different time history analyses defined. And the first one has got a certain value of a multiplier and a certain time in which this load acts upon the model. For the second one, we have the situation that the value of load is twice larger, but the analysis time is twice shorter. And the third one, we have 2 times smaller load, but the time is twice longer. So that's interesting that when we go to the results and we go to the time history diagrams, okay, we first may have a look at the forces, and you can see that that area under each of these diagrams exactly the same, that correspond to the energy of this object. And when we now replace them with displacements, you can see that actually the results, despite the fact that time history analysis have been defined with different parameters, are exactly the same. So, okay, let me go back to the cable. So first we open the model with all cables defined, and I will calculate that because I need to determine the value of force in the cable that then we're going to remove from the model to simulate that it breaks. All right, so what I'm going to do, I'm going to select all the cables, okay, and then I go to the diagrams and will display value of forces with values. And to see the better which forces correspond to the cables, I'm going to just filter the display to the selection only. So we have 11.11 axial force in the top cables. All right, so I will now open the same mast, but this time with one of the cables removed. Okay, so in the first load case, we have this force 11.11 that represents the missing cable, but also there is another load case defined with the force of the same magnitude but acting in the opposite direction. So if we look at the time history analysis defined here, look that this is nonlinear time history analysis, so only 2 methods are available. So this starting case, case number 1, is considered as the initial, and then we have the cable, we have the force in the opposite direction applied with constant value for a certain period of time. And okay, if we go to the results, and if we go to time history analysis diagrams, we can see the displacement of the top of the cable. It looks like this. But we may also add the display of forces in the cables. So axial force in the cable that is on the opposite side of the cable that we removed, and also the axial force of the cable that is on the opposite side. So I will move them. Okay. So you can see that the situation is that when the force in one of these cables increases, the force in the cable being defined on the opposite side actually decreases. So if we go back to the view, we can see which elements they were selected. 1603, 1607. It's okay. So the cables on the opposite sides of the mast. All right. So another field of application of time history analysis is the dynamic effect of moving vehicle or train. Again, let me switch back to robot and load the example. So in this example, we have a number of static load cases that represents our vehicle, train, and we have time history analysis with the functions defined in such a way that the load is constant, meaning that when one load is terminated, the other load starts. I mean, or has its peak value, so that the constant total load value is at the same level. And if we go to the results, if we go to the time history analysis diagrams, we can see all these functions. And maybe I will switch off automatic range. I will select a certain part. You can see that this load stops, this load starts, and this load is when the previous load starts and the following ends and the following starts, has got its peak value. And well, let me see that we actually may have also the display of reactions, how they change through time, and we select, for example, a supporting node 102, and we can see how the reaction in a given peer changes along the change in the position of the vehicle. Okay, let me go back to slides. You may also try to determine the efficiency of the tuned mass damper, for example, by exporting results to Excel, where you can create a diagram as shown on this slide. And you can compare of maximal displacements with damper and without the damper. So let me show how to define such damper in robot. So I will switch to robot again. I will open yet another example. This is the model where we don't have the damper defined. Okay, we have some excitation force defined in case 3, okay, in node 12. And this time we have a number of time history analysis that corresponds to the points that were shown on the diagram created from Excel, and each force has got a certain forcing function. And if we have a look at the displacements for a model without a damper, and we in the table add the maximum value, you will see that this values corresponds to the peak, to the middle range of values that were defined on the slide. So if we go to the slide, okay, so this value corresponds to this red line. Okay, so if I now open the model where I have the damper defined, we'll see the difference this damper makes. But before we look at the results, let me show how the damper was defined. So we have a compatible nodes defined here under the force. And if we go to the definition of compatible nodes, you can see that there is a certain elasticity and certain damping defined between these two nodes. And now, if we just display the same results, displacement of node under the force, you'll see that if I go to table columns and I will add the maximum value, this value are much lower, and they actually corresponds to these green points on the diagram. This may be useful, especially for models with, the modeling earthquake using the time history analysis may be especially useful for models with strong nonlinear behavior, when you cannot use the response spectra analysis, but you have the accelerogram which defines the earthquake. You can either use the virtual directions load cases that I described on one of the previous slides, having the accelerogram or define forcing functions for static load case with imposed displacements, velocities, or accelerations of a node where you have support. So let's see that in robot. So if we open a model, okay, this is the model that actually stands for bottom part, for the foundation part of the structure, and the structure is defined as additional, a missing structural, not modeled part of the building is modeled as added masses, okay, defined in this way. And if we have a look at the time history analysis, you can see that there are three direction cases that I mentioned before that are designed for modeling earthquake with time history analysis. And if we have a look at the functions, you can see that there are three different functions, three different accelerograms define each of the directions. And if we go to points, you can see how this looks like. And for the accelerogram, there is the possibility to open that from the text file. Text file being just two columns with the horizontal axis representing time and vertical representing the acceleration. So if we go to open from file, we may use, for example, the function that is predefined in robot, and we may, for example, instead of the function defined in this example, decide on a different function. So, for example, for the direction x, I may select the function that I opened from the file and modify it. Okay, so let me open again this example, this time with calculated results. Yeah. And if we go here, we can see that we have number of components, and you may actually convert one of these components into a virtual load case, as I mentioned on one of the previous slides. So if I press the create case from component, you can see that we have got this load case where we haven't got the physical loads, but we may see the results as for standard load case, for example, bending moment map. And we can use this component for design of reinforcement or for design of steel structure. Okay. Yeah, this is exactly the slide that describes the conversion of the component into a load case that can be used for design. Something that we just done. And finally, I'd like to encourage you to use these links to learn more or find solutions for the problems that you have got with robot. And now please feel free to ask questions about the webinar. I'll try to answer them.
Thank you, Arthur, for the presentation, and we would like you to write your questions in a questions panel of GoToWebinar window, and we will answer them as soon as possible.
Alex, there is a question about the links to the previous webinars. So the easiest is to just go to Robot Forum, and one of the top topics is named Robot Webinars, and it includes all the links to the webinars. So just it is as easy as typing in your Google search robot forum, Autodesk Robot Forum. You can directly find the webinar topic at the top of the list, and then you'll have all the links that you need to the previous webinar. there's no question, so I don't know whether the topics was so easy or so difficult. Anyway, of course, you can use the robot forum for providing the feedback or just asking the questions that you may want to ask later or after running some examples of time history analysis on your own. So right, if there is no further questions, I would like to invite you for the next webinar. That's going to be for moving loads in robot. And I would like to thank you all for attending this webinar. See you again in a month.